Have you ever stood on a station platform as a massive train thunders past and just wondered, how on earth do these colossal 100-ton machines avoid colliding with each other? Well, welcome to today's Explainer. We're going to completely decode the hidden mechanics keeping mass transit safe. We're looking at the invisible shield of railway safety engineering. It's a fascinating world where danger is literally, systematically engineered right out of the equation.
Okay, let's take a quick look at today's agenda. We'll start with the integrated system and then walk through 4 core principles: safe spacing, speed control, route holding, and conflicting moves. Finally, we'll wrap up with the really incredible fail-safe concept.
All right, part 1. The integrated system, more than just brakes. So, absolute safety, or what engineers actually define as freedom from unacceptable risk, requires a massive interconnected organism. Safety is delivered by integrating products, processes, and people into a unified system. I mean, you can't just slap good brakes on a train and call it a day, right? You need an entire control and communication system dictating exactly when those brakes must be applied. It ensures that human operations and mechanical systems function together as one unified shield.
Moving on to Principle 1, safe spacings. Because trains obviously can't swerve, and, well, they take an incredibly long time to stop, the track ahead is divided up into designated sections. We call these blocks. Now, the golden rule here is that only one train is allowed in a block at any given time. Notice how the signals behind the train step down, from red to yellow to double yellow to green. That spacing isn't just random guesswork. It's strictly, mathematically calculated based on the maximum braking distance a train needs to safely come to a complete halt before hitting an occupied block.
But modern technology takes this a massive step further. Traditionally, we relied on fixed block working, where those track sections were just static hardware points. But with modern communication-based train control, we use what's called moving block working. Think of it like driving with a highly advanced radar. A central system calculates this dynamic, safe bubble around the train in real time. As the train slows down, its required braking distance shrinks, and so does that bubble. It's brilliant, really, because it allows trains to run safely much closer together, instantly increasing the overall capacity of the line without sacrificing even a drop of safety.
Next up, Principle 2, speed control.
Inside an automatic train protection, or ATP system, data is constantly in motion. Take a look at the red line. That's the maximum safe speed profile. The system is continuously calculating this curve based on upcoming signals, track gradients, and the train's own unique braking capabilities. That blue line, that's the actual speed of the train. As long as the driver keeps the blue line safely tucked under the red line, we're golden.
But what happens if they don't? Say a train approaches a danger signal way too fast, or maybe takes a curb too aggressively. The system doesn't just ask nicely for a slowdown. No, it intervenes sequentially. First, it hits the driver with a continuous warning. If they ignore that, the system automatically triggers a brake intervention to forcefully bring the speed back into that safe envelope. And if a train actually blows past the danger signal, the system enters a trip state. It literally cuts power and forces a complete, unoverridable halt. It's all about protecting everyone on board.
Okay, Principle 3, route holding. You can think of this procedural locking mechanism exactly like deadbolting a heavy front door. Before a train is ever given a green light, the system double-checks that the movable rails, known as points, are in the exact right position, and then it locks them. Once the train gets the authority to proceed, those tracks ahead are physically and electronically secured against any alteration. That lock is strictly maintained until the system actively detects the train is passed completely clear of the section.
Now, what if a human signaler just makes a mistake? Imagine they try to cancel a green light right as a train is flying towards it. Well, that's where this crucial subsystem, approach locking, kicks in. If a train is past the point of no return, meaning, it's physically moving too fast to stop before the signal, the system just flat out refuses to release the route. It guarantees that the rug cannot be accidentally pulled out from under a fast approaching train.
Which brings us to Principle 4, conflicting moves.
Interlocking is the real brain behind this principle. It's much like a traffic light at a busy road intersection that physically cannot show green in 2 opposing directions at once. The railway interlocking mechanism mathematically prevents catastrophic junction conflicts. It literally stops the system from ever generating the authorization for 2 trains to occupy the exact same section of tracks simultaneously, no exceptions.
By constantly assessing the entire track layout, the system builds an impenetrable shield around the authorized train. When it sets a route, it automatically locks out any directly opposing routes.
It prevents indirectly opposing routes where trains might cross paths further down the line. It even secures what's called flank protection, meaning it anticipates and blocks rogue movements from adjacent converging tracks. Before the train even arrives, the entire environment is completely neutralized.
And finally, the overarching philosophy, the fail-safe concept.
The sheer brilliance here is the fundamental assumption that failure is inevitable. Cables are going to snap, power will fail, software will glitch. Railway engineers don't waste time trying to build a system that never ever breaks. Instead, they engineer a system that breaks safely. That is the fail-safe principle. Any credible failure must absolutely automatically drop the system into a more restrictive, safer state.
So the golden rule here is, when in doubt, stop. If an interlocking computer crashes or a massive storm knocks out the power grid, the system doesn't just freeze on a green light. The default zero-energy response is always the most restrictive state possible. That means immediately returning all signals to a red danger state or automatically applying the brakes to any trains currently in motion.
Let me give you a really brilliant practical example of this in action. The track circuits that detect where trains are, well, they rely on a continuous electrical current running right through the steel rails. When a train rolls over the track, its metal axle creates a short circuit, and the system registers the track as occupied. Now, what if a vandal cuts the wire or a component just burns out? The continuous current drops. To the computer, that broken wire mimics the exact same electrical state as a 500-ton train sitting on the track. It literally forces the system to report the track as occupied, instantly halting all traffic headed that way.
It's just an incredibly elegant solution to the chaotic realities of the physical world. Let's conclude our explainer today by pondering this. We have successfully engineered a mass transit system where the actual literal failure of the equipment practically guarantees the safety of human life. So where else in our modern, complex world, from our financial systems to our power grids, could we revolutionize our security by assuming failure and engineering the system to break safely? Think about it. Thanks for watching, and keep questioning the world around you.